Hello everyone, myself Chaitanya Kumar and I'm from Department of Electrical Engineering IIT Madras. I'm going to take the fourth tutorial based on week 4's content of analog electronic circuits. So let's start. Let's start with a little bit of a recap of what we did in this week. So in this week, we basically tried to emulate various kind of controlled sources using the basic building block of the modern day analog electronics, that is a MOSFET. So we started with a voltage controlled voltage source. So for voltage controlled voltage source, what we need is we need the input, that is Z in, has to be infinity as and why it needs to be infinity, because it needs to sense the voltage at a particular node, and if something is to sense the voltage at a particular node, it should not draw current from that node, otherwise it will result in voltage drop at that particular node. So V in has to be infinity and Z in has to be infinity, and the output voltage, that is output impedance, that is has to be Z out, has to be for an ideal VCVS has to be 0. And why? Because ultimately it's a voltage source, and voltage source ideally should have 0 output resistance, so that if it is connected to a non-zero or non-finite output load impedance, it should not suffer with voltage drop. So we found out with the help of the standard feedback operation, we found out that the common drain amplifier meets with this criteria. So we the small signal equivalent, the small signal model for the common drain amplifier is this thing. So we have a load over here that is of value RL, and the input is applied V in over here, and the drain is connected to the AC ground, and the output we take at the source of the MOSFET. So if you see Z in, as we can see, is infinity, and Z out, to calculate Z out, what we will do is we will ground the input, and this is how our circuit will look. We have RL over here. Now if we apply a test current, let's say at this output node, that is the source node, some current will go into or for that matter, let's apply a test voltage over here. The test voltage that we apply at the source of this node will result in the sum of the current will come from go into the RL, that will be Vt by RL. And since we can see that we are applying a voltage to the source terminal of a transistor, and the gate terminal is grounded, so the current that will be flowing from the drain to the source of the transistor will be Gm times Vg minus Vs, and our Vg is equal to 0 and Vs is equal to Vt. So the current that will be flowing from the drain to the source of the transistor will be minus Gm times Vt. So in actual direction, actual direction of the current will be from source to the drain of the transistor, that will be Gm times Vt. So the total current I test that will be flowing from Vt will be equal to, so I test is equal to Vt by RL plus GMVT That implies Vt comes out as common 1 plus GMRL divided by RL. And if you calculate, so our Z out is basically Vt by I test, that is equal to RL upon 1 plus GM RL. Now, if GM is very high, or let's say GM RL is much greater than 1, then this can be approximated to be equal to RL upon GM RL, that is equal to 1 by GM. So we can see that as the transconductance of our transistor, that is GM, keeps on getting higher and higher. That means our transistor is getting becoming more like an ideal device. Our common drain amplifier behaves as a common drain amplifier's output resistance goes to 0. And let's see what is the gain from input to the output. So gain from input to output is, we have RL over here, V in, V out. So again, the current that will be flowing down will be V out by RL. The current that will be flowing from the drain to source of the MOSFET will be GM times VGS. VG is V in and VS is V out. So V in, GM times V in minus V out. If we equate these two currents, because there is no other path for the current to go, if we equate these two currents, what we get is GM times V in minus V out is equal to V out by RL. That implies V out by V in is equal to GM RL upon 1 plus GM RL. And if GM RL is much greater than 1, then our gain almost becomes equal to 1. So we have a voltage controlled voltage source whose input impedance is infinity, output impedance is 0, and the gain from input to output is equal to 1. Now one would argue that what about so how can we make voltage control voltage source with a gain larger than 1? So there are two ways to, let's see what can be done for that. So generally gain larger than 1 or gain other than 1 for that matter. So here you can see that the maximum this gain can go to is unity. That is when GM of the transistor is infinite. It can't go more than that. So what if you want gain that is more than unity? So in that case, what will you do is you will use there are two. So let's talk about two circuits that with which we can achieve that. So generally, we have seen that gain greater than unity can be achieved using a common source amplifier, and the common source amplifier we see looks like this. We have V in over here, and let's say there is a load resistance connected over here, and we have we take the output resistance and then we take the output at this node, that is V out. Okay, the gain from input to output, and if the transconductance of this transistor is GM, the gain from the input to output is basically GMRL minus of GMRL. We can see that we have the gain from input to output, and and if we choose GMRL to be a value greater than 1, then we can say that we have got a gain. No, we have got a device that can give you gain greater than 1. But the problem is, again, the input impedance is infinite. For that matter, input impedance is still infinite, but the output impedance is not infinite. Let's see what the output impedance is. If we look output impedance from here, so the looking up impedance is RL, and in parallel to that, looking in impedance, let's say it's a transconductor without transistor without any output resistance. So its looking out impedance will be equal to looking in impedance from this node, that is from drain, will be equal to infinite. So your Z out is equal to the load resistance RL. No, what we can do over here is we can cascade it with. This does not serve the purpose of zero output impedance. So zero output impedance can be we can get by actually like placing a common drain amplifier that we saw, whose gain is infinity. Gain is unity at the output of the common source amplifier. In this way, we can cascade it. So we have RL over here, we have V in, then we have a common drain amplifier over here, and we can take the output over here. So let's say this is a common drain amplifier with infinite GM. So its gain will be a unity, and this is a common source amplifier. Its gain is minus GMRL. So overall, we get the in cascade, our gains are multiplied. So minus GMRL into 1, we get the gain as minus GMRL. The input impedance from here is infinite, and since there is no loading from the common drain amplifier over here, so here there won't be any additional loading. So at least as far as DC is concerned, the gain here will remain unchanged, that is minus GMRL. And at the output, since it's an we are assuming it to be an ideal transistor, its output impedance will be 1 by GM, will be which will be approaching to 0. So this is how you can make a VCVS with ideal with gain greater than unity, or gain other than unity for that matter. But again, the problem over here is that the gain depends on your transconductance, that is GM, and the value of GM varies a lot with respect to temperature or other VT, the threshold voltage variations and all. These things you don't want in your circuit. So what we will do is, so another way to get a gain where the your gain does not depends on the GM of the actual transistor, and it basically depends on a ratio of two things. So we saw the common drain amplifier. The common drain amplifier had an AC short at the drain side, and input was given to the gate side. The source side had a resistance of, let's say, a value of R1. And if we took the uh, output over here, if GM is large enough, the output was GMR1 upon 1 plus GMR1. This was roughly equal to unity if GMR1 was large enough. So if this output is equal to 1, equal to V in times V in, and this is roughly equal to V in, That means the current that is flowing through this resistor, and ultimately the current that is flowing from the source to drain of the transistor is V in by R1. This is the same current that will flow from the drain side also. So this current is right now flowing directly from an AC ground, so there is no voltage change at this drain side. But if we introduce another resistance over here, let's call its value R2, then the voltage drop across R2 will be the current that is V in by R1. The current that is V in by R1 multiplied by the resistance. So we get voltage drop of V in by R1 times R2, voltage drop across this resistance R2. There is 0 on one side, so the voltage at the drain node will be minus V in R2 by R1. Depending, so by manipulating the values of the resistors R1 and R2, we can calculate the actual gain. We can get the desired gain, and now it does if the transconductance is large enough such that Gm times R1 is much greater than unity, so the gain won't depend on the value of the transistor's transconductance, that is Gm. If we take the output over here, then we will get value of minus V in times R2 by R1 as our output. And again, the output resistance over here unfortunately is not in 0, so we can cascade it with another common drain stage, which will give us 0 output impedance. So this is how you can build the voltage controlled voltage source. So this was as far as small signal analysis was concerned. In large signal as far as biasing of the system is concerned, the common drain amplifier CDM CDAMP is biased. Basically, if let's say this voltage is held to a constant value of Vg, and this is connected to some voltage of VDD. So if we pull out a current of let's say I bias from this network, from this voltage, due to the self biasing, due to the source biasing, this voltage will automatically be set to Vg minus V overdrive plus Vt. Okay, in DC conditions. So this will be a self biased circuit, and to maintain to fix this to a fixed voltage of Vg, we can use a resistive divider. And if we use resistive divider over here, let's say R1, R2, and it goes from VDD. So there, with resistor divider, the value of Vg is set, and we have the bias current I bias. It goes to VDD. So this is making our biasing network, and after that we can have coupling capacitors over here, C in and C out, which for the desired frequency ranges, C in and C out will be shorted, and we can give the input as V source to one side and take the output from the drain side at the load resistance RL. So this is the complete circuit of common drain amplifier. Next, after this, we saw current controlled voltage sources. So how do we build current controlled voltage sources? So CCVS. Now, the characteristic of CCVS is its input impedance should be equal to 0, and your output impedance should also be equal to 0. Okay. Okay. So, let's see how we can build it. We saw that what we wanted is okay. Before we go to that, this all this analysis that we did for voltage controlled voltage source can be all this analysis that we did for a voltage controlled voltage source can be quickly done by the fact that we that by the concept that we discussed in the first tutorial, that is if the circuit is in negative feedback and your gain of any kind of control source, a MOSFET in active region in small signal analysis is a controlled source. So if its gain goes to infinity, then the controlling terminal becomes 0. So in common drain amplifier also, in CD amp, if we look it that way, so RL over here, this is Vin over here. So in common drain amplifier, if the GM, and we know that due to the source, there is self biasing at source when we have degeneration. The transistor is there in a negative feedback, and if its GM goes to infinity, it's a controlling terminal, that is VGS, has to go to 0. So if VGS goes to 0, that means automatically we can say Vin should be equal to Vout. So without actually doing applying KCL, KVL, and getting the answer, we can actually quickly get the answer as Vin equal to Vout if we apply the concept of transistors. If we apply this concept. Now, after this, we have current controlled voltage source. So, input impedance has to be 0 and output impedance also has to be 0. Why we need this? The input impedance, since we are going to sense the current, if there is any element that is sensing the current, that means current should go through that element, and if it has some impedance of its own, that means it will create a voltage drop across it, and if it creates a voltage drop across it, it will disturb the functioning of the actual circuit. So we don't want that. In order to sense the current, where do we sense it? The we discussed in it was discussed in detail, like how the circuit came up by. But the circuit looked somewhat like this. You had some I bias over here, and in DC circuit, in the incremental, you had open circuit at you had short circuit at the source side. You were taking the output from the drain side, and you were applying the current to the gate in, and you were getting output at B out. So let's quickly go through how do we let's quickly go through the math, like how we get the values of Z in, Z out, and the gain, that is AV. So those things, if we go through, we won't go through the actual algebra. We can clearly see that the circuit is in negative feedback. How the circuit is in negative feedback? Let's say, to analyze the negative feedback of a circuit, you can de-energize all the external sources that are being applied. So we can take this circuit, since we are applying a current source over here, we can de-energize that, and that means the circuit becomes an open circuit. So what we have over here is this circuit. Now there is some since this is so this is an so in incremental picture it looks like this. In We assume that our MOSFET is present in active region of operation, and like its job is basically to make sure that there is no incremental current. Again, I will put stress on this fact. Make sure that incrementally your drain side is an open circuit. That means there is no incremental current that is going to flow through there. There will be a biasing current that will be flowing through this transistor to keep it in active, to keep it in saturation region, but there won't be any incremental current on top of that due to changes in the circuit. So that's what its job is, if we are saying that the MOSFET's drain is open circuit in incremental analysis. So let's say this voltage V over here tries to increase. If the V tries to increase, that means the gate voltage Vg also tries to increase. That means there is some current that tries to flow through this transistor, that is Gm times Vg, and that current since there is no other path for the current to flow, it will start pulling the voltage. It will start There will be some parasitic capacitance at each node in practice, so it will start pulling the voltage of this node down. So this circuit, when there is a connection between drain and the gate of the transistor, the circuit is behaving in negative feedback. And if the circuit is present in negative feedback, then your and why it is so? Because it is trying to reverse the effect of any stimulus applied to the circuit. So we know now that this circuit is behaving in negative feedback. And if the circuit is behaving in negative feedback and the GM of this transistor goes to infinite, so in that case your input uh, so VGS has to go to zero. The transistor will make sure that your VGS is equal to zero. And what do you mean that by VGS being equal to zero? That means so VS is already grounded. It's an AC ground. So that implies VG also has to be AC ground. And if this voltage cannot increase, so this voltage has to be will be maintained by this transistor's negative feedback action to zero. And if that is the case, now this current that is being injected to the gate of the transistor, it can't flow inside the gate, as the gate resistance is infinite. It will try to flow through the resistance R. And if current flows through resistance R, the voltage drop across it will be I in times R. So output will be equal to minus of I in times R. And of course, this is the gain that you get, the current to voltage gain that you get, or other way we can say the trans impedance. So R is basically trans impedance of the circuit. So basically, you given a current of I in that is converted into voltage of value minus of I in times R. So it gives you some current gain. Now let's see if its impedance is as required. So this is the circuit that we had. So if we try to push in, as we see, if we try to push in any current into this circuit, no matter what current we push into the circuit, the source voltage, the gate voltage will be fixed to zero. And if the gate voltage is fixed to zero, so that means to say any current that I push won't change the voltage at the gate input side. So our input impedances equal to 0. For output impedance, again, if we try to push, let's say, some I test into the circuit, all this I test, so where will this, and the GM of the circuit is still infinite. So if the GM is infinite, this circuit is still in negative feedback. So this will be maintained at VG, and all the current will flow through the transistor. And since the transistor has infinite GM, so it can sink as much as current as it wants without actually increasing the controlling terminal, that is VGS. So we will actually go other way around also, solve this and get the actual output resistance and show that if GM tends to infinity, its value will be its impedance will be zero. So in both the cases, the actual impedance that we get is Zn is basically equal to 1 by Gm. Why 1 by Gm? If you try to toggle this node by some current, let's say, so this current all has to flow inside this transistor, and if all this current has to be supported by the transistor, so there will be a voltage that will be developed, since the source is grounded to zero. So to support the current of I in, the voltage, the current has to be equal to GM times I in. So let's say this was I in, the current, all this current will be the pushed into the transistor, and the transistor's current we know is GM times VGS. S is 0, so it's equal to basically GM times VG, that is equal to I in, and hence our Zn is equal to 1 by Gm. So this is how we get the input current. With the same logic, we can get the output input resistance. With the same logic, we can get the output resistance of the circuit. So we see that in both input and output impedance is equal to 1 by Gm. And if the Gm of the circuit tends to infinity, our both the input and output impedance become zero. So it basically uh, caters all the three needs, all the requirements for a circuit to be a current controlled voltage source. Its input impedance has to be zero, its output impedance has to be zero, and it should provide some current some trans impedance gain, and the trans impedance gain that we get from the circuit is equal to R. Again, we see that as we saw in the previous cases in voltage controlled voltage source also, we devised voltage controlled voltage source whose value does not directly depends on GM. Same is the case over here. The value does not directly depends on the GM. If the GM of the transistor is high enough, its value just depend on a passive element, that is of value R. And as far as biasing of this circuit is concerned, so it can be basically current bias circuit, VDD, and here we can apply some I in. This will be I bias, and we can take the output at the source of this circuit. So this is how we can, this is one way to bias. Of course, it can be biased in multiple ways. This is one of the ways to bias the circuit. So this is the story of current controlled voltage source. Now we see voltage controlled current sources. So voltage controlled current source is basically, we need the input impedance to be infinite. The output impedance also has to be infinite, as it's a current source. Current source need to have infinite output impedance, and of course it needs some trans conductance gain from input to output. So it's the same way that we so again it's a common drain amplifier. We have V in at the gate of the circuit. It's not basically a common drain amplifier. It's like a version of common drain amplifier. So there is some load resistance to which we need to supply current controlled voltage controlled current source with some kV in. So we discussed in so it was discussed in detail like how the circuit comes about. The circuit is basically RL over here, R1, then some V. So basically what we have is uh, it's some it's another some additional circuitry over the common drain amplifier. So we know that from the common drain amplifier analysis, we know that the gain from input to output is equal to 1. So V in has to be equal to V out. Again, this transistor is in, so this current source is also in negative feedback. So if the output is equal to V in, the current that flows through the transistor is equal to V in by R1, and same is the current, that is I out, that flows through the load resistance. So the current we get as V in by R1. Again, the voltage to current gain that we get is again independent of the independent of the transconductance of the circuit, and we it only if the transconductance is large enough, it is equal to 1 by R1. So this is what we get, and then again input impedance is equal to it's the gate of the, since the input is applied to the gate of the circuit, so input impedance is infinite. The output impedance, the output is taken from the drain of the circuit, so as long as there is no channel length modulation, our output impedance is also infinite. So this clears the criteria of it clears the criteria of the circuit being a voltage controlled current source. And as far as biasing of the circuit is concerned, uh, it can be done in following way. So the like there can be multiple biasing techniques with like any of the biasing techniques that we have read so far can be used to uh, bias the circuit. So then we have current controlled current source. This is the last one. So current controlled current source, again the input impedance has to be equal to 0 as we are sensing the current. The output impedance has to be infinite as we need a current source over here. So for this we use common gate amplifier. We understood in class how the circuit comes about. So the gate is an AC ground. There is a current that is pushed inside as I in over here, and the same current can come at the output of the transistor R node. So the gain of this current controlled current source is unity, that is equal to 1. And again, the input impedance, as it's the looking in impedance from the source side, it's equal to Zn is equal to 1 by Gm, and if the Gm is tending to infinity, this is roughly equal to 0. The output impedance Z out, it's the impedance looking in from the drain side of the transistor, and if there is no channel length modulation, output impedance is infinity. And then we have the input impedance is 0, output impedance is infinity. We have a current controlled current source with a gain of unity. Now let's say we wanted a current controlled current source with the gain other than unity. In that case, what we will do is we will use the concept of current mirrors. So how does a current mirror works? So we have a current that is flowing through, let's say, a current source of I in. We need to sense this current. Now, sensing current, again, we need zero input impedance. We will use a diode connected transistor over here. This will basically, if it's a Gm tends to infinity, the current that will be flowing through, so its input impedance Zn will be equal to 0, and so we have Zn equal to 0 if Gm is tending to infinity. Now this current can be taken and multiplied over here as so let's say its aspect ratio W by L is some X. So this aspect ratio W by L can be taken as alpha X, and we will get a current of value alpha times I in that will be flowing through this transconductor. So with this, we can make current. So there are more details you will learn about the circuit going later. With this, you can basically get a gain greater than unity. Now, we after this we covered. We dwelled started the introduction of a finite output impedance of a transistor. So, finite output impedance of the transistor, basically, we looked at one of the building blocks of our circuits. So, let's say, and we did this particular calculations previously also. Let's say the gate is grounded. There is resistance R1 at the source of the transistor, and we are to calculate the looking in impedance from the drain side of the transistor. If let's say there was R, the output resistance was infinite, then our Z out would have been infinite. But if there is some output resistance of value RO, then we discussed previously also, and the math can be done. The output impedance Z out becomes GMRO times R1 plus RO plus R1, that is roughly equal to GMRO times R1. So, instead of infinite output impedance, we get a finite value, and it also has impact on the gains of the gain of the it also has impact on the gains that we get in the control sources, which will be dealt later in the next week. So, without going into further into the finite output impedance line, I will in the rest of the tute I will like to build up more on the concept of control sources. So we know that uh, we have discussed till now that if a controlled source has infinite gain and it is present in a negative feedback, then the controlling terminal of that particular controlled source can be the controlling terminal, the controlling parameter of that particular current source will go to zero. So, with this concept, we'll try to analyze a few circuits and see and try to verify this concept on a few circuits. So, we have a circuit over here. The input is given to the input of this resistor R1. This is grounded. This is a value I1. It is some K times I1, and there is this resistance R2. We need to find its. So this is the first circuit. The second circuit is V in R1. There is some V1 over here, some K times V1, and we need to find the output voltage V out. Third is R1 V in I1 minus K times I1. So this is a current control voltage source R2, and the output V out. And the fourth circuit is V1 minus K times V1 R2 and this thing. So we'll try to find out the gain from input to output in all the four circuits in both the scenarios when the gain of the control source is finite, and then we will see what happens if the gain of the control source becomes infinite. So let's start from the first circuit. So as we can see that a current is being sensed, and a current is being pushed into the circuit as well. So this is a circuit based on a current controlled current source. So let's see what is the what let's see what is the gain, what is the gain from input to output. So as this particular node is connected to ground, so whatever current that flows through this resistor R1 will directly flow into will directly flow into will try to directly flow into this particular terminal that is of ground. The current that will be coming from here, it will be equal to V in by R1, and the current that will be going through R2 will be K times I1. So we can say that I1 is equal to V in by R1. Applying KCL at node G, I1 is equal to V in by R1 minus K times I1. Okay, that goes to say that I1 times 1 plus K is equal to V in by R1. That means I1 is equal to V in by R1. So if I divided by 1 plus K. So if this is equal to I1, so this is the same current that is flowing. K times this current is flowing through the current controlled current source, and that is the current that is flowing through R2 as well. So output resistance V out can be written as minus of R2 times K times I1, that is equal to minus of R2 times K times V in upon K plus 1. Okay, so V in by R1 times K plus 1. So this can be modified as follows: R2 by R1 K upon K plus 1 times V in. So if K tends to infinity, that is the gain of the current source, gain of the current controlled current source tends to infinity, our output becomes V out is equal to minus of R2 by R1 times V in. Now let's try to see like using the original argument that if the circuit is in negative feedback, the any current across any across any controlled source, uh, if the circuit is in negative feedback, the controlling parameter goes to 0. Let's try to use this argument to find out the gain of this circuit directly. First of all, let's see whether this circuit is in negative feedback or not. Once. So let's have a look on the circuit whether it is in negative feedback or not. Let's say this voltage tries to go up due to some disturbance. V tries to go up. If V tries to go up, the current that is being that is flowing, the current I1 also tries to, the current I1 that is flowing inside this terminal also tries to go up. And if this current tries to go up, the controlled current that is K times I1, that is basically pulling the current out of this node, tries to go up. And if the current that is pulling the current that is coming out of this node tries to go up, this particular node will come to a will try to go down. So basically, this circuit is trying to reverse any stimulus applied to it. Hence, the circuit is in negative feedback. And if the circuit is in negative feedback, the controlling terminal has to go to zero. That means I1 is supposed to go to zero. If I1 equal to zero, so we have R1, R2, K times I1, and output V out, V in, and this is I1. And K is infinite. If K is infinite, the circuit is in negative feedback. If the circuit is in negative feedback, I1 goes to 0. And if I1 goes to 0, uh, and but this voltage, since there is this voltage is equal to 0, the current that will be flowing through R1 will still be V in times R1. Since I1 is 0, so no current can flow, no current out of V in times R1 can flow inside this node. So all this current will flow through the resistor R2, and there will be a voltage drop across R2 will be R2 times R2 by R1 times V in, and the output, so V R2 will be R2 by R1 times V in, and one side is 0. So V out will be minus R2 by R1 times V in. So from here we see that this if this so we see that this particular node of the circuit behaved as a high impedance node despite being actually grounded. And what was the reason for that? The circuit being in negative feedback. And if the circuit is in negative feedback and the gain is infinite, the gain of the controlled source is infinite, the value of the gain from input to output we get as minus R2 by R1. Now let's check the second circuit. In this circuit, node V1, so node so the current that will be flowing from this R1 R2 network will be, let's call this I1. So I1 is equal to V in minus V out upon R1 plus R2. Okay, this is equal to K times V1, or V in minus V1 V in minus V1 upon R1 plus R2 is equal to K times V1. That is the current that is being taken by the current source. And the other way to write this, so sorry, R1 is equal to K times V1. This is also equal to V1 minus V out by R2. And V1 by voltage division, by superposition and voltage division, can be written as V in times R1 by R1 plus R2 plus V out times, sorry, R1 upon R1 plus R2 if we substitute it in the above equation, we get V in minus V in R2 upon R1 plus R2 plus V out R1 upon R1 plus R2 is equal to K times V1, which is also this equation. So that implies V in upon K plus 1 is equal to V1, and V1 from here and here can be equated. That implies V in upon K plus 1 is equal to V in R2 plus V out R1 divided by R1 plus R2. Just a minute. This is K times R1, sorry. Hmm. So V in times R1 plus R2 is equal to V in times R2 times R1 K plus 1 plus V out times R1 times R1 K plus 1. So from here, one second. We will try to solve it again. I think there is some misunderstanding in this. So let's go about it again. V in minus V1 by R1 is equal to the same current that is being pulled out from the current controlled voltage controlled current source. This is equal to K times V1. That implies V in is equal to K times R1 plus V1 plus 1 times V1. So V1 is equal to V in upon KR1 plus 1. Now we know V1. So what is V out? V out is equal to V1 plus, sorry, V1 minus. So this is the voltage V1. The voltage drop across R2 will be I1 times R2, and V out will be V1 minus I1 times R2. V1 minus I1 times R2. So we can take, so this is basically equal to V1 minus K V1 times R2, that is V1 times 1 minus K R2 is equal to V out. And what is V1? V1 is equal to, V1's value can be substituted from here. So V out is equal to V in upon k R1 plus 1 divided by 1 minus k R2. So this is the value of V out by V in we get as 1 minus k R2 divided by 1 plus k R1. Now again, if k tends to infinity, we get value as minus R2 by R1, V out by V in. Okay, so again, the same principle, this is how we solve this circuit algebraically. But if we see, if we apply the principle that we have, if we apply our concept, so what we have is, if the circuit is in negative feedback or not. Let's check if the circuit is in negative feedback or not. So if this voltage tries to go up, if V out tries to go up, that means V1 will try to go up, this value will try to go up, and if V1 tries to go up, that means K times V1 current will try to go up, and this current is basically being pulled out of this node V out. So this will result in V out going down. So this means that the circuit is in negative feedback. And if the circuit is in negative feedback, so the controlling parameter, that is V1 has to go to 0 if k tends to infinity. Okay, so if that is the case, so we have R1 over here, R2, so this node will be equal to 0, and if this node is equal to 0, the current that is flowing is V in by R1. The same current flows over here also, and the output becomes minus R2 by R1 times Vn. Now let's go to the third circuit. That is made with a current controlled voltage source. So again, we will try to find out the voltage, the V in by V out by V in. So if we calculate it over here, the current that will be flowing from here will be V in by R1. This will be V in by R1, and the current that will be going out will be, the current that will be flowing in this direction will be V out by R1, V out by R2. So the I1 will be equal to V in by R1 plus V out by R2, and due to that, the output voltage, that is the output of this current controlled voltage source, will be equal to minus of k times I1, that is V in by R1 plus V out by R2. So our equation becomes V out times 1 plus k by R2 is equal to minus of k times V in by R1. That implies V out by V in is equal to minus of K times R1 divided by 1 plus K times K by R2. So again, if K tends to infinity, okay, we'll write it in a more K by R1 R2 plus K. So over here again, if K tends to infinity, our value becomes minus R2 by R1. And this can again be seen from this circuit being in negative feedback. So to analyze whether the circuit is in negative feedback, let's ground the input. So if V out tries to go up, that implies I1 tries to go up, that implies minus K times I1, that is equal to V out, tries to go down. So this circuit is again in negative feedback. If the circuit is in negative feedback, so the circuit is in negative feedback, and if the circuit is in negative feedback, then the controlling terminal, that is I1, will go to 0. If I1 is 0, so V in by R1 is equal to minus of, or what was I1 actually initially? V in by R1 plus V out by R2. That implies V out by V in is equal to minus of R2 by R1. Okay. Now let's take the fourth circuit. So over here we have a voltage controlled voltage source. Our current from this side is V in minus V1 by R1, and our current from this side is and this is equal to V1 minus V out by R2, and V out of course can be written as uh, V out we have as minus K times V1, so substituting that, V in minus V1 by R1 is equal to V1 plus K times V1 by R2. That implies V in equal to V1 1 plus K by R2 plus V in by R1 is equal to 1 plus K by R2 plus 1 by R1. So V in so V1 can be written as V in times R2 upon 1 plus R2 plus 1 plus K times R1. That implies V out, that is equal to minus of K times V1, can be written as V in times minus of V in times R2 times minus of R2 upon R2 plus 1 plus K times R1 times K. Okay. Again, if K tends to infinity, V out by V1, V in becomes minus of R2 by R1. So again, this can be seen through, this can be derived through the concept of the circuit being in negative feedback. So let's see whether the circuit is in negative feedback. If so again, if V out tries to go up, that implies V1 tries to go up, that implies minus K times V1 equal to V out tries to go down. So of course the circuit is in negative feedback, and if the circuit is in negative feedback, that means uh, V in R1 V1 is equal to 0 minus K times V1 R2, and we have V out over here. So if V1 is equal to 0, the current that is flowing from here is equal to V in by R1. The same current flows through here itself also, and so the voltage drop across R2 is R2 times V in by R1. So output voltage is minus of R2 times V in by R1. So if we compare the, so we see that in all the four circuits, the circuit was a negative feedback, and we had the same gain irrespective of whatever control source we used. So if we go to the circuits above as a summary, so if the k is tending to infinity in all the four cases, I1 will go to 0. In the first case, I1 will go to 0. The current through this resistor R1 will be V in by R1, and the output will be minus R2 by R1 times Vn. In the second case, V1 will go to 0. The current from here will be V in by R1. The same current will flow through R2, and output will be minus R2 by R1 times Vn. In the fourth circuit also, I1 will go to 0. So the current, that is V in by R1, will flow through R2 also, and output will be equal to minus of R2 by R1 times Vn. In the fourth circuit, again, negative feedback, K goes to infinity, V1 is equal to 0. The current from here will be V in by R1, and the same current flows through R2, and V out then will be equal to minus R2 by R1 times V in. So we see that, and what is this minus R2 by R1 times V in? This is basically the gain of a inverting amplifier, V in and V out. So, with from this particular example, we see that the op amp with high negative gain can be replaced by any of the four controlled sources we have, and as long as the gain is infinite, it doesn't matter. The always the gain from input to output of this inverting amplifier will be equal to minus R2 by R1. This was all that I intended to say in this tutorial. Thank you for watching.